In the previous video, we looked at media that conduct signals that enables computers to communicate with one another. However, not all communication occurs via media that conduct such signals. In many cases, the signals are simply radiated or sent through the air. In fact, there was a theory many years ago that this empty space, what we would probably call the air nowadays, around us, was filled by a special substance, and that was called the ether. And this is where the name Ethernet comes from, because radio waves and other waves that were sent through this nothingness around us was assumed to be sent via the ether. Today we know much more about what constitutes the air, the atmosphere around us. But in this video we will not focus too deeply on the physical properties of this substance. We will rather look at the categories of signals that can be transmitted without a specific medium to carry it. That will include electromagnetic waves and various forms of light. In fact, we already developed the taxonomy for this exploration in our previous video. And in this video, we will simply continue with that taxonomy, but on the radiated media side of the taxonomy. Light can be used to communicate. In days gone by, very often people synchronized their cell phones with their personal computers by means of infrared light. Only remaining remnants that we really see around nowadays are television controls and so on. They enable one to communicate between this remote control and the television. The earlier examples would actually have exchanged data, and most cellular phones and laptops were equipped with infrared ports. Obviously, infrared is not visible to the human eye, but what you see in the insert is a little bit of a demonstration where a camera has been used that is able to capture the infrared light and render it visible, so you can get some feeling for what it looks like when it is emitted by a remote controller. In addition to infrared light, lasers can be used to communicate. Lasers are a much better option. They are in fact used for high-speed data communication, and your only restriction is really line of sight. So as long as you can direct a laser at the recipient, then that laser can be switched on and off, and the recipient many kilometers away can see the laser being turned on and off and can receive the signal. Obviously, to get return traffic, you'll need lasers in both directions. What we've done in the insert is we've captured a little bit of laser light just from an ordinary laser pointer passing through smoke, so that you can get some sort of a feeling for what it looks like. In general, works quite well. Yes, if you do get an obstacle that blocks the light, then you do have a problem. But under normal circumstances, lasers are quite effective to communicate. Microwaves are also used for line-of-sight communication. Radio masts are often located at post offices or other telecommunications providers. Now, you should remember that in days gone by in South Africa, telecommunication services were provided by the South African Post Office. That's why you will often see these telecommunication dishes on sites where the major post offices in a town are located. If you look up the tower, then you will see dishes, parabolic dishes, that are attached to those towers. And they will then send a signal from one dish to the other. Again, the restriction is line of sight, so you cannot send it through a mountain or through a building. And therefore, it is better to have these towers rather high. Picture that you're seeing now is the Lucas Rand tower that is used for data communication. The nice thing about it, like any other such tower, is that it is located physically very high, and therefore it is unlikely that there will be any obstruction between the transmitters, the dishes that are located on it, whether they are transmitting or receiving signals. The next point on our agenda is satellite communication. Satellite communication works on the premise that there are satellites orbiting the Earth, and you have Earth stations, very often in the form of a dish, and they can then transmit a signal to the satellite, and the satellite can transmit that signal or relay it back to another station somewhere on the Earth. There is one type of satellite that is of particular interest to us, and those are the so-called geostationary satellites. So the way that they work is, as the Earth turns, they will orbit at exactly the same speed. So what it means is, if the satellite is, let's say, above Africa and the Earth turns, it will remain above Africa. It will be stationary in terms of that location on Earth, wherever it happens to be parked. What's actually happening, of course, is everything's turning, but relative to one another, everything remains static. To get a satellite to rotate at the same speed as the Earth, as the speed at which the Earth rotates, you need to have it 36,000 kilometers in the air. If you think about the Earth, diameter is about 12,000 kilometers, so you need to get it about 3 times the distance of the diameter of the Earth away from the Earth. So it is really, really high up in the sky. Another restriction is that the satellite has to be above the equator to remain stationary, to rotate at the same speed as the Earth. In days gone by, I was told that you need a 4-degree separation between satellites, so that would mean you could only fit 90 of them in. At the moment, there are about 400 of them above the equator, so clearly they have managed to put them closer and closer together over time. One of these geostationary satellites that is particularly interesting to me is the one that is known as TDRS 11. That is the tracking and data relay satellite number 11. Now, before it was launched, it was known as TDRS-K. After it was deployed, it was renamed to TDRS 11. It is used by NASA, and it is used for NASA communication purposes, in particular for the International Space Station and similar objects in space. So freighter rockets or the Hubble telescope, they can communicate to these TDRS satellites, and the TDRS satellite can then relay those communications to the Earth. The TDRS 11 is situated at 171 degrees. So if you take Greenwich to be more or less the front of the Earth, then at 170 degrees west, you are basically at the rear of the Earth, and it is sitting just about there over the Pacific Ocean. Let's look at the NASA videos when TDRS was launched. It was launched at the end of January 2013. It was the evening of the 30th, but they tend to take the launch time in terms of universal time, and therefore the official launch time was very early in the morning of the 31st of January 2013.
Attention all stations, this is the NLM on the NLM net. We are in good configuration with the launch vehicle. Centaur prop loading is complete. Booster LO2 loading is complete. The range is green. Weather is acceptable at this time. I would now like to conduct the final launch readiness and spacecraft configured for launch poll. NASA CE.
NASA CE, go.
SMA.
SMA's go.
SMD.
SMD's go.
NASA MEM.
NASA MEM is go.
NAM.
NEM's ready.
NLM copies. The NASA team is ready for TDRS-K launch.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And liftoff of the Atlas V rocket with TDRS-K, broadening, enhancing, and improving the capability of space-based tracking.
Here is the best picture that I could take during the launch. As you can see, one is quite a distance from the spacecraft when it is launched. In fact, there's this nice countdown that you've seen on television in the movies. And then this spacecraft just suddenly shoots up into the sky and it's gone. And then the sound reaches you, the sound of the spacecraft leaving. Another satellite that is interesting for us is Intelsat 20. Intelsat 20 is sitting at 68.5 degrees east. So it means it's sitting there more or less between Africa and India. Intelsat, it has nothing to do with Intel Corporation, who manufactures chips. It is a name that just happens to sound similar, and they are used for commercial purposes. In fact, there is a second Intelsat that is also interesting for our purposes, and that is also sitting at that same spot. So the separation that I spoke about earlier, we definitely have to look at that when we consider these satellites. Here we have Intelsat's website, and we want to look at their network. In particular, let's look at the satellite fleet. There you can see a couple of the satellites that happen to be positioned over the Atlantic Ocean. You can see the names of the various satellites, and you can also see where they are, east or west, and some information about the bands on which they communicate. I am at this point interested in those that are positioned over the Indian Ocean, and there is Intelsat 20 that we mentioned a moment or two ago. If you look at the description on the side here, then you can see that it can communicate in various bands. Those are just various frequency bands that can be used. And at the top, you can see that it can communicate using C-band. C-band is one that is used for wide Earth coverage. A typical satellite can cover about a third of the Earth at a rather slow speed. But one satellite covering a third of the Earth, so 3 satellites, and you've got the whole Earth covered. The more interesting ones for our purposes are probably the KU frequency bands. Those are in what is known as the K band, but specifically the underside of the K band, so the lower frequencies in the K band, or the frequency just under the K band. There's one that jumps out at us, that is the KU band for South Africa. And if we go and look at the coverage that we are getting from that, you will see that that transponder is focused, or those transponders are focused on South Africa. The measurements that you see there, the decibel watts, are indicators of the strength of the signal. So you can see that there's a very, very strong signal over South Africa, and then it becomes weaker as it spreads out. The reason why it is interesting for our purposes is that I guess the most popular satellite television service uses that satellite to transmit to South Africa. And if you look at South African rooftops, you will see the satellite dishes all pointing towards the satellite. More specifically, if we go and look at the key parameters of the satellite, then you will see that it has in the C-band 24 transponders, but then in the KU band there are 60 of them, and you can see that some of them are pointing towards Europe and Africa, some of them towards Europe, Middle East, some of them towards Russia, and then specifically some pointing to South Africa. Looking at the C-band, you can see that the C-band covers absolutely everything at a much lower power, but it covers right from South Africa, or from Africa to Australia. This one doesn't cover the United States. For that you need another satellite. What you can see on this picture are the various satellites that belong to Intelsat, and you can see that they are spread above the equator, but you can see that some of them are just off the equator. Now, we were interested in ones that were positioned towards India, somewhere between South Africa and India, and there you can see Intelsat 36 at 68.5 degrees east. If we click on that, you get the C-band. Now, almost parallel to that, there is Intelsat 20, so on the equator, just below number 36, and clicking on that takes us back to the one that we looked at a moment or two ago. So one that is in daily use to transmit to South Africa. The geostationary satellites, as we said previously, remain static above the Earth relative to the Earth. Another option are the so-called low Earth orbit, or LEO satellites. Low, they are much lower. They're not 36,000 kilometers away from the Earth. In fact, they are about 800 kilometers above the Earth. Now, being 800 kilometers above the Earth means that they will rotate at a very different speed. In fact, you will see it, if you could see that far, you'd see it rising above the horizon and sitting at the other horizon. And what that means is you cannot rely on it being present at any given moment. So what you in fact need is not a single satellite that orbits around the Earth at a low altitude, but a whole constellation of them. So that if one happens to be above you, you can use it, but as it moves away, another one moves into place. And one of the best known projects of this type is the Iridium Project. Iridium was chosen as the name of this product because the atomic number of iridium is 77, and that is the number of satellites that they expected to need in a constellation above the Earth to cover the whole Earth. So the way that it would work then is that your Earth station, and we'll look at what we mean by that in a moment, your Earth station will talk to a satellite, and let's say you are in South Africa, you'll talk to a satellite that is more or less above you, and that would then relay to another satellite and relay to another satellite, and you can speak to someone who is somewhere else on Earth. Obviously, if it covers the whole Earth, what makes it nice is if you're in the middle of the ocean, it will still work. In the end, there are not 77 Iridium satellites deployed. There are about 66 in the constellation, but they also have a couple of spares that are orbiting the Earth, so that if anyone fails in a way, then one of those spares can be moved into position. A moment ago, we spoke about your Earth station. Now, that was a very big name for what we are actually talking about. If you only need to be able to talk about 800 kilometers into the air, something much, much smaller can do the work on your behalf. And here you see typical handsets. These happen to be the Iridium products. I'm not trying to endorse them, it's just that they happen to be some of the original projects in this genre. There are a number of competitors, but you can see that they look like 1990s cell phones, handsets that are rather bulky compared to a normal cellular phone, but nonetheless something that you can carry in your hand. If you are sailing from one point to another on the open ocean, then taking one of these with you and being able to communicate is no problem whatsoever. You can also use something that works like a modem, so that you can connect your laptop to the satellite. One of the technical specifications, these also function, and by these I mean the products, as well as the satellites in the constellation, also function more or less in the K frequency band. More specifically, they function in the Ka frequency band. So that's the frequency band that is just above the K frequency band. So you talk about wavelengths of about 7 millimeters to 1 centimeter. We're currently talking about satellites, but there is a much cheaper alternative that has emerged and that plays a similar role, albeit a less permanent role. And that is the sort of thing that is done by Project Loon. Loon comes from the word balloon, so they launch transmitters or transponders using a balloon, and then it would use the wind direction to drift over a continent. You can adjust the height of the loon, and that could steer it in a different direction. And where these are particularly useful is when a disaster happens and you need to deploy communication facilities over a broad area quickly. Looking at flight radar, we can see that traffic has increased significantly over southern Africa from what it was in the recent past. I can only see one loon over Africa at the moment. And in fact, if we zoom in, we can see it's not a single loon, but 3 loons hovering over Mozambique. If we ask for more information about one of them, then you will see there is a description or a picture of what it looks like, and it points you to Project Loon. Clearly, lots of air traffic crossing the Atlantic, and quite interesting how busy it is in the United States. But even there, you can see that there are a couple of loons deployed. Going to South America, there you can see more of these loons deployed, and here in Peru at the moment, also quite a couple of them deployed. So clearly mountainous terrain, not the easiest of places to install other types of communication, but there they are, and they're able to communicate with one another as well as with earth stations. Very often it's your typical Wi-Fi type of signal that you would use to communicate with them. So no special earth station or no special handheld equipment necessary to work with them. So there are clearly a couple of options of having a relay station overhead, whether it's a geostationary satellite, a low Earth orbiting satellite, or a balloon of sorts. They all offer you the ability to talk over a very long geographical area, and in some cases they enable you to get them installed in a very, very short duration. When we talk about Wi-Fi, most of you have a pretty good idea what we are talking about. For many of you, it has become a utility. You simply want to turn on the cell phone, pick up the Wi-Fi signal, and use it. Those are somewhat more technically inclined may have a picture of something like this, typical Wi-Fi access point in mind. Here is one example, here is another example, and lots of antennas and so on that we may have to think about. But if we think about a box like this, it is typically a box that contains a fair amount of intelligence, in quotes. This particular one has a hub, or a switch rather, at the back. There's another plug there that is intended for DSL use. So this, on top of the switch and the Wi-Fi capabilities and the routing capabilities that we have not even mentioned, it also has a ADSL modem built in. And in terms of the routing functionality, this typically also serves as a NAT box. It will translate whatever addresses you're using on the inside to your public IP address that you're getting from the service provider. This model is pretty similar. Again, a series of plugs at the back. In this particular case, there's no DSL plug, but there is an option that you can plug this into a router that goes to the outside world. However, on the face of this, there is an indication that this has an LTE modem built in, so cellular capability, and indeed there is a SIM card that enables us to communicate to the rest of the world. The equipment like this very often nowadays for the past many years have software built in that act as web servers. So the typical way in which you would configure them, the typical way in which you would enter your passwords and everything would be to access these boxes using a web browser. In one of the earlier videos, I showed you one of the access points that I've deployed in my house. This is a much simpler device. In this particular case, antennas are hidden on the inside, so nothing's sticking out. And basically one socket there, and that is for a PoE Ethernet link, so that I can link it to my network and it will power it. And exactly how one uses this, we will talk about in a moment or two. We should, while we're discussing Wi-Fi, be talking about a range of technical issues. The number of antennas, the range that you can reach with Wi-Fi, the manner in which signals are modulated, and so on and so on. But yet again, those are engineering aspects, and we won't be able to say too much about them in any case. Let's now look at how this is used in more detail. What makes this setup somewhat different from the previous examples, the examples that I said you are probably familiar with, is the following. Where those examples included a lot of software to, for example, drive a web server so that you can change the setup and so on. The software for this latter access point is running on a computer. So that can be one of your own local computers. It can also be somewhere in the cloud out there. It just depends on how you set it up, how you configure it. In my case, it's configured to run on my local computer. And what I have opened here at the moment is a management window to that computer that is running the software that controls the access points. So the access points are rather unintelligent devices, and the intelligence is running on a central server. What you can see on this particular display is that there are two LAN switches that operate in the same way. So the LAN switches also don't have much internal software. The bulk of their intelligence, in quotes, comes from what is running on the server. And there are 6 wireless access points. And those then are the ones that are interesting to us right now. So if we were to zoom in on the devices, then you will see that those are the 6 access points. I can also ask that it displays my 2 switches, but those aren't the things that I'm interested in right now. I'm interested in these access points. And I'm going to try and enlarge the scale a little bit. It should make it somewhat easier to read. And what you can see there are the IP addresses, then the various statuses of the access points. You can see the type of access point. In fact, the top 2 that you see there are the switches. So I'm going to set it so that it only shows me the access points right now. So those 6 access points are displayed. And what you can also see there is under that heading clients is the number of clients that are connected to each of these access points. So we've got one here at the bottom that is currently driving 7 or has 7 pieces of equipment connected to it, whereas quite a couple of the others only have 2. Then in the next column, I can see the downlink, how much data has been transferred from the access point to various devices. And just above that, I can see the uplink, how much data has been carried from devices to the access point. The channels that are currently in use, for the first one that is listed there, you can see that channel 7 is in use, and that is for 802.11 N and G, and channel 128 for 82.11 AC. And the same for, as you go down that list, you will see which channels are used for N and G and which channels are used for AC. Now, if I, for example, want to look at the details of a specific access point, then I can simply click on it, and you can see that this particular access point that I've selected now is not particularly busy. On the N and B and G spectrum, or part of the Wi-Fi selection, it's about 5% busy. At this moment, it doesn't have anything in the NA or AC specifications connected to it. If I look at the detail, then you can see that this uplink is a wired full duplex 1 gigabit per second cable that runs from it. And then if I want to look at the specifications of the radios, there is the radio that is used for N, B, and G of Wi-Fi, and the various statistics. You can also see how busy it is in terms of how many transmission retries we've had, how many transmission or dropped packets we had in terms of transmissions, also in terms of reception and so on. So not a very busy access point right now. It will grow significantly busier later today. So that was the radio for N and G, the radio for AC. There are the specifications for that particular one. Again, not going to try and delve into all of this, but I can also look at the performance and so on. If I were to click on clients there, then I'd be able to see exactly which clients are connected to that access point. If I were to click on configure, then I can configure various aspects of it, and tools will give me various debugging options, including a debugging terminal where I can do some things on the command line. Not much. But the whole point of what I'm trying to show you here, and I know this is a very superficial demonstration, is that the software for these devices are not running on the devices. The control for these devices are not on a per device basis. So since it's controlled from a central perspective, it's much easier to collaborate. It's much easier to hand over one piece of equipment as it moves through the building to another access point. And it gives me a single window on exactly what my Wi-Fi situation is. Couple of these devices you may have seen, let's just get that out of the way. You may have seen that in terms of the model names, that one is an LR, that's a long range, but most of these access points are the light versions, so they don't transmit very far. So hopefully it means that I am not broadcasting too far away from my house. Most of them have limited power, and then I have multiple access points to cover the limited space. And that will hopefully add a little bit to the security in terms of the visibility of the setup that I have here. These are not all of my access points, but these are the bulk, and over time I'm moving all the other access points over to this system. The logic behind what you've just seen is that these devices, these access points, that are in principle hardware with some software embedded in it, suddenly becomes rather dumb hardware, and the software installed in it becomes more intelligent, and it runs on a separate computer. And what we are beginning to see there is a concept known as software-defined networking. We haven't looked at the switches, but in terms of the switches, you can also provide multiple lines, multiple physical connections, virtual LANs through those switches, so that one port may be connected to another port, let's say port 1 connected to port 3, and port 4 connected to port 5, but they are not interconnected, they are separate, even though it's the same physical piece of machinery. Software-defined networking allows one to create networks without changing the topology, without changing the physical arrangements of machines, and yet achieve the same results. Moving on from Wi-Fi, it is time to talk about cellular communications. Cellular communications has been used over decades now for communication. It used to be a very, very expensive data communication option, but as time progressed, it became more affordable and faster. One of the elements of the various generations that we've seen is simply an increase in speed. So from the first generation that wasn't really intended as data communication equipment, to the second generation, to the third, to the fourth, to the fifth generation, and so on, all of those have always increased the speed, capacity, the bandwidth of the medium to higher levels than it used to be. But it's not only the speed, it's also the nature of the network that changed. With second-generation networks, the network itself was digital, but you typically dialed up a connection. So you established the connection and you paid for it per time unit, per second or per minute. But then edge technology moved in, and suddenly we had packet capabilities, and you began paying for the quantity of data that you transferred. That made it possible to be permanently connected with a low quantity of data being transmitted at a very affordable price. However, as technology moved on, even the cost per packet has dropped to the extent that many cellular connections nowadays are uncapped. In other words, you pay a fee for the facility, and beyond that, your data communication, the actual data that you transmit, does not incur any additional fees. This is the Wikipedia page on mobile telephony. And here we get a brief summary of the different technologies used by the different generations of mobile telephones. In many cases, those technologies were not necessarily used in one particular country because different countries adopted different standards. 1G is not listed here. It was an analog standard, and particularly in South Africa, we did not see 1G ever used. 2G was the first digital standard and was rather popular in Europe and also in South Africa, and that is GSM. GSM was augmented with various technologies that moved it sort of closer to what was eventually known as 3G. So the addition of something like GPRS and a little bit later Edge increased the speed, but also allowed the use of data packets that were not possible under ordinary 2G technology. And those were sometimes referred to as 2.5 or 2.75G to indicate that they were moving away from a pure circuit switching network and also away from a pure voice network to something where data packets could be transmitted. 3G networks, apart from the ever-increasing speed that we see with all these generations, used UMTS in our case, and it is 3G is in essence a digital network that also happens to carry voice traffic, whereas 2G was clearly a network that was intended for voice but happened to carry digital traffic. The emphasis shifted in 3G to become a technology that worked in a digital fashion and could carry voice as well. With 4G, the first contender for the 4G title was LTE, long-term evolution. And this was seen as the way in which GSM could evolve for future use. There's a big debate about whether LTE, the original LTE, indeed meets all the requirements to be a 4G network. There are many people who would argue that LTE Advanced is the first technology to achieve that status as a proper 4G or fourth generation network. What you see under the 4G heading are the LTE and LTE Advanced that are commonly used in South Africa, but you also see the WiMAX standards. And the difference between the two is that LTE is like its other family members, the GSM family members, intended to be used while on the move. WiMAX, on the other hand, is a wireless technology that is intended primarily for stationary communicating parties. So it's a wireless technology that you would use to install at an office complex or a house and then achieve high-speed wireless connection to a service provider some distance away from you. And then the big new game on the block is 5G. Again, there is the concomitant increase in speed. But with 5G, we are really talking about a data network where voice just becomes yet another application. Along with 5G, you can see some of the names or some of the terms that have become rather well known over the last couple of years. Things like MIMO and beamforming. Those are low-level physical characteristics that enable these networks to communicate much, much faster. In principle, maintain the high speed and the quality of the connection even as the distance increases somewhat. However, don't think that it will stop at 5G. We will see further generations as time goes by. In this video, we looked at the various wireless or disconnected or unconnected technologies. We specifically used the term radiated because a term like wireless implies that the other technologies would use a wire, and in this case, very often light is used. Also, in the connected or conducted case, light may be used. The question between this video and the previous video is that in the previous video, a conductor was used to guide whatever signal was sent to its destination. In this video, we looked at technologies where the signal may have been directed, like a laser, but there was no conductor that took it to its final destination. The signal in what we discussed in this video could also be broadcast, sent out to multiple parties at the same time. In the final video that remains, we will look at a couple of other physical aspects of networks that need to be considered when one builds a network.
Music you're listening to is completely electronic.